Hello, everyone. How are you now? Welcome to this 2021 digital workshop hosted by Campbell Scientific. My name is Keith Garrett. I'm the Director of Technology at Mount Washington Observatory. I'd like to thank Peter Gagne, our instrumentation specialist, for some help with this presentation. Allow me to start with our mission statement. Mount Washington Observatory is a private, nonprofit, member-supported institution with a mission to advance understanding of the natural systems that create Earth's weather and climate. It serves this mission by maintaining a weather station on the summit of Mount Washington in New Hampshire, performing weather and climate research, conducting innovative science education programs, and interpreting the heritage of the Mount Washington region. Mount Washington Observatory's mountaintop weather station is the core of the institution. Staffed continuously since the organization's founding in 1932, it's operated by two alternating crews who live on the summit for a week at a time, taking hourly weather observations, performing research, and conducting educational programs. Weather observations are reported to the National Weather Service for use in nationwide forecasting models and regional reports. Observatory scientists produce specialized forecasts for the higher summits of the White Mountains and Greater White Mountain region. In this image, you'll see an example of one of our forecasts. You can find that on our website at mountwashington.org. With detailed climate data dating back to the organization's founding in 1932, Mount Washington Observatory maintains what is now one of North America's longest continuous climate records. The photo on the right is our number 2 anemometer, which recorded a record of 231 miles per hour in 1934. In addition to weather observation, the observatory utilizes state-of-the-art summit facility as a benchmark research station, collaborating with universities, government agencies, and private companies on many types of weather and climate research. Recent projects have studied rime ice formation, air pollutant trends, the effects of climate change on high-altitude environments, global tropospheric chemistry, and low-cost temperature monitoring of the snowpack. Striving to advance understanding of atmospheric and climatic processes and their impacts on the northeastern U.S. ecosystems, Mount Washington Observatory conducts collaborative research that encompasses multiple scientific disciplines. In this photo, researchers from Plymouth State University in New Hampshire assembled the prototype low-cost snowpack temperature station in Tuckerman Ravine on Mount Washington. The observatory also conducts testing for consumer and industrial products such as sonic and mechanical anemometers and serves as an integral partner in the development, testing, and monitoring of scientific equipment. Located 6,288 feet above sea level with immediate access to the extreme conditions of the alpine zone, Mount Washington Observatory also partners with manufacturers to conduct product testing. Our Mesonet offers a variety of locations for the testing and development of sensors and equipment. Along with our Summit Weather Station, Mount Washington Observatory maintains 18 Mesonet stations across the White Mountains region of New Hampshire. The harsh and varying conditions of the White Mountains create unique challenges operating and maintaining this network of stations. In the photo, you can see an overview of our stations across New Hampshire, as well as a few of our more prominent stations across Mount Washington. In the image, you'll see stations labeled 2300, 3300, 4000, and so on. That's our Autoroad vertical profile, and those stations are important for the rest of this. So why does Mount Washington experience extreme weather? As Mark Twain said, if you don't like the weather in New England, now just wait a few minutes. New England is the tailpipe of America. Regardless of where these weather stations originate, most systems end up in New England. The White Mountains are colder than the surrounding terrain, with Mount Washington being the most prominent peak for a distance of over 1,000 miles. The White Mountains are nearly always windy due to topographic acceleration of winds over the summit. This image shows the most common low-pressure system tracks from 1981 to 2010. With the assistance of Joshua Campbell and Campbell Scientific, the construction of the Mount Washington Regional Mesonet began in about 2003, with the development of the Autoroad vertical profile. The Autoroad vertical profile is a series of stations spread across the 8 miles of Mount Washington Autoroad every 1,000 feet of elevation gain. This layout acts as a permanent weather balloon. From 2004 until the present, an additional 14 stations were added with a few removed, covering approximately 150,000 acres and spanning a wide range of regional climates, from New Hampshire's temperate valleys to the alpine summits. The typical Mesonet site consists of a power source, mounting structure, Campbell scientific data logger, communications devices, one temperature sensor, and one combination temperature and relative humidity sensor inside naturally aspirated radiation shields. Optional sensors measure wind speed and direction, ground temperature, barometric pressure, ice and freezing rain detectors, and solar radiation. Common extraneous devices may include a network switch, IP webcam, uninterruptible power supply, solar charge controller, Campbell Scientific relay, various fuses, circuit breakers, and lightning arresters. Data loggers and processing equipment are normally located inside Campbell Scientific environmental enclosures. This is a view inside our 4,000-foot Autoroad vertical profile station. Inside, we can see a FreeWave serial radio, CR10 pack bus data logger, power buses, a charge controller, and a PS100 power supply. 11 sites are solar powered, while 5 are on AC power. At AC power sites, a Campbell Scientific PS100 or PS150 power supply powers the data loggers in case of a line power outage. At the solar-powered sites, the data logger utilizes an A21REL Campbell Scientific relay to shut off all devices except the data logger in order to preserve DC power, for the weather instruments only. Campbell Scientific assisted with code for determining sunrise and sunset times throughout the year for optimal power consumption. The relays turn off webcams as well as other equipment during dark hours. Data can be collected later once the voltage is recovered to an acceptable level. Some sites are 12 volts DC, others are 24. This is mostly dictated by the power requirements of the components. The observatory uses gel AGM 240 amp hour batteries placed inside insulated wooden boxes at most of our solar stations. Our Wildcat Mountain Station contains 8 of these 160-pound batteries, as it is used as an important communications relay for our Mesonet. This is an example of one of our battery enclosures. The insulation is intended not to retain heat in the compartment, but to deaden radical temperature swings. Wiring is generally routed to the lee side of the prevailing winds, which in winter are out of the west or northwest, and secured with zip ties and/or electrical tape. We will also wipe down power cabling with WD-40 seasonally in an attempt to mitigate rodents chewing through exposed wiring, which, as you can imagine, does not make the stations very happy. Care must be taken to account for ice load buildup on any wiring bundles, and service loops are used to prevent melting ice, fog, or rainwater from running into sensitive areas. This fall, all of our zip ties broke on a service loop, and the end result was a stream of water flowing down a power over Ethernet cable into our enclosure, destroying the network switch and a 5.8 gigahertz radio that it was connected to. All of the remote Autoroad vertical profile sites along the 8-mile Mount Washington Autoroad are mounted to Campbell Scientific tripods and secured to the ground. 2 lower sites use spikes driven into the softer ground. The tripod legs at 4,000 feet and 5,300 feet are bolted to very heavy concrete blocks with embedded threaded studs, and the 4,300-foot site, being located on top of a large boulder or ledge, required holes to be drilled into the rock in order to insert expanding anchors. Other sites utilize either a simple mast attached to a building or a round tower. A few of the other higher locations. These are notable to me as I am not a big fan of heights. Don't like these. In the left photo, our station at Attitash Ski Area. The site was built on top of a 60-foot cell tower. There is no power available to this site, and large batteries had to be hoisted to power the station. On the right, at our Cranmore Ski Area station, it is atop the uppermost lift tower at the summit. A unique issue with the lift configuration is the constant vibration of the sensors while the lift is in operation. The observatory uses CR10X pack bus, CR10s, and CR1000s and CR6 data loggers across our entire network. The Autoroad vertical profile sites, being the first of the remote stations to be built, all use CR10X pack bus. They have been in continuous use for 15 years and have proven to be so impervious to the weather extremes that there has been no reason to replace them. They are also extremely power efficient, which is most important for the Autoroad vertical profile because of the lack of sun in winter. Sierra 1000s with integrated NL115 Ethernet interface devices are used everywhere else. NL115s also provide compact flash storage so that we can collect data while the station is in a low power state. We have just recently started using Sierra 6 loggers in our locations on the summit. One is used with our prototype pitot-static tube anemometer and another with a sonic anemometer. We do have plans to deploy Sierra 6 loggers across the autoroad vertical profile. IP radios in the 900 MHz, 2.4, and 5.8 GHz spectrum provide the bulk of communications between stations. We're currently phasing out 900 MHz as advances in the higher frequency efficiencies have allowed us greater throughput and distance capabilities. The observatory currently employs units from Freewave, Trango, Deliberant, Mimosa, and Ubiquity. The longest shot is 17 miles from our administrative office in North Conway, New Hampshire to the summit of Mount Washington, utilizing Mimosa B5C 5.0 GHz radios. These B5C radios allowed us to increase our speed from 18 to 30 megabit to a wonderful 1.3 gigabit across 17 miles. The average length of all the other Mesonet links are about 5 to 10 miles. Newer, faster radios are being deployed to keep up with increased data density as camera resolutions improve. More pictures are taken for smoother time-lapse videos, and the possibility of user-controlled live video becomes closer to reality for our members. Again, we are member-supported. A few data loggers still communicate via serial over Freewave radios. However, we're in the process of deploying TCP/IP radios to most locations along with upgrades to our battery banks. A test station in Tuckerman Ravine utilizes an Arduino-based data logger and an ESP32 815 MHz radio, communicating with a Raspberry Pi over a distance of 6 miles, creating an extremely inexpensive solution. However, it is very delicate. There are stations that do not have line of sight to any of our stations or the summit. These are the Cannon Mountain and Appalachian Mountain Club Highland Center sites. We no longer utilize sonic walls. In each of these cases, we use Cisco Meraki VPN gateways to establish a reliable connection over the internet. These have proven to be very effective methods of establishing safe and secure network connections as we branch out further from Mount Washington. The configuration of site-to-site VPN using this method is nearly automatic. A number of different weather sensors have been used throughout the years and replaced as they have become discontinued or failed. At this time, the observatory employs Campbell T107s for the temperature and CS215s for temperature and relative humidity. The two temperature sensors must agree within 0.2 degrees Fahrenheit to confirm that the data is valid. Calibration data from each sensor is also ingested as correction factors in the database. Mounted inside naturally aspirated radiation shields, they are protected from the sun, wind, and rain. However, we do have a few fail each year from heavy ice loads. Wind measurements are recorded mostly by RM Young 05105, Alpine version 05105-45s, and Alpine HD 05108s, mechanically operated. They are calibrated in-house at most every 2 years by technical staff. Alpine models are used wherever severe winter icing occurs, such as our outer road 4,000-foot station. Our anemometer at 5,300 is taken down in the winter as it would never survive the ice and wind there. Wildcat and Hermit Lake at Tuckerman Ravine stay up year-round. However, we get frequent icing at Wildcat Mountain, which affects the anemometer. Due to the excessive severe icing that regularly occurs at Cannon Mountain, a Taylor Scientific heated anemometer and vane must be used. We are fortunate to have AC line power at that station. Maintenance and upkeep of the Mesonet stations in the White Mountains is necessary and constant. Extreme rain, cold temperatures, hurricane force winds, penetrating fog, massive ice accretion all put tremendous strain on the equipment. This is a good view from our 4,000-foot station. Sometimes it is beautiful out, which is really nice. This station also regularly sees 100-mile-an-hour plus winds. In the spring, we have to visit all of the sites and assess the damage from the winter, make plans to acquire materials, and arrange to repair, replace, and/or upgrade equipment during the summer months when sites are more accessible and easier to work on. Fall is the time to prepare the stations for the winter's extreme conditions. We try to get to the ski area sites before they shut lifts down for pre-winter maintenance. At 2 of the sites, we are allowed to drive up the mountain roads as long as we have 4-wheel drive and plenty of height to clear the water bars. Utilizing the Mount Washington Auto Road via car or truck to prepare the auto road stations is much easier before snow and ice occurs, which can be as early as late August. Once ice is prevalent on the road, we must use tire chains on our 4-wheel drive trucks and passenger van. Sometimes we even have to use double chains when the ice is particularly nasty, what we call boilerplate. The ride up and down can be interesting, and maybe scary is a better word for it, but definitely interesting. In typical years, by the end of October or early November, the full-size Bombardier BR-275 Snowcat is used as the snowpack encroaches on the mountain from the top down. Most of our mountain winter transportation uses the Snowcat. For the sites that have no other access, we have to walk. Appalachian Mountain Club hut sites at Hermit Lake, Misfit Springs, Lake of the Clouds are solar sites that are hike-in only. What we take on our backs. We always travel in pairs for safety, plus having a helper is always handy. We have to watch the weather very closely, especially above tree line, as the weather can change in a flash with little warning. Get in, get the job done, and get home safely is a good day in the Whites. The furthest walkable sites are about 2.6 miles one way, so meticulous planning is key before a single step is taken. Everything needed, down to a tool, a nut, a bolt, or even a string for snaking wires, must be brought along, or the work may not get done and a visit may have to happen again. Besides ice, snow, and wind, penetrating fog is one of the fiercest adversaries we do battle with. High winds drive the fog into the smallest gaps of our equipment. This is a major problem for the summit as well as the Mesonet, so the proper use of mastic tape is critical. We use 3M88 electrical tape on most RF connections. It's an 8 mil thick tape. It's very durable, especially in the cold. Lower grade electrical tape quickly becomes useless below 20 degrees. It either snaps or it doesn't stick. With the good tape, wrap the first layer normally, then spin the roll 180 degrees and wrap the opposite direction with the sticky side out. Then spin it back and finish, while shingling the tape in the proper orientation in order to shed moisture. After much trial and error, this method has proven very effective. We also use zip ties abundantly to secure cables and wires. Cheap ones become brittle very quickly and just break in one's hands. Quality zip ties from a company like Thomas & Betts are worth the extra cost. Some of the more recent crazier things we have encountered in the Whites. A tree limb fell on one of the tripod legs and bent it so severely the aim of the radio antenna was off. The snow and ice was so severe at 4300 that a mini glacier formed right above the station. As it slowly ground its way downward, it ripped the embedded lag bolts right out of the rock it was situated on and destroyed the tripod. Small ice loads and heavy winds on our tripod for our Campbell electric field meter folded the mast in half. And just for contrast, this small video or photo is of our COG Railroad 4,500 foot elevation station, showing it's not always horrible weather, and sometimes we get fun transportation methods to the summit or to the Mesonet stations. And it is definitely a unique ride if you've never taken that train. Using our Mesonet infrastructure, Mount Washington Observatory is capable of delivering high-speed internet access to locations where it would otherwise be unavailable. An example of this is in Tuckerman Ravine, where the U.S. Forest Service and Appalachian Mountain Club has high-speed internet access. We're also able to route our IP phones to provide telephony service to most Mesonet sites. A useful tool for mapping wireless coverage and speeds is the Ubiquiti Link Mapper, available at link.ui.com. The photo on the left shows an example of line-of-sight coverage mapping using this link tool. The right photo shows a remote camera at our 4,300-foot station that we use to monitor travel conditions in one of the more precarious sections of road. Many stations host webcams providing the viewer with a real-time view of the conditions around Mount Washington. Currently, our system provides still images and full-day time lapses to members. The infrastructure now exists to provide live camera feeds from several stations that we hope to have available to Mount Washington Observatory members in 2021. This is a recording from our camera on Wildcat Mountain looking at the flanks of Mount Washington. It's an Axis P5635 PTZ camera, which we have internal access to for the live high-definition streams. With Campbell Scientific data loggers at each site, we're able to monitor equipment for those who may be hosted at the same locations. This is our shared solar location on Tyrol Mountain in Jackson, New Hampshire. This site hosts our standard weather station equipment and a live camera, as well as hosting power monitors for the local fire department repeater. Until recently, we have also monitored battery capacities for the U.S. Forest Service locations around the Whites. Real-time data is available to stakeholders online for self-monitoring, as well as our own internal monitoring of station status. This is just another example of one of our Mesonet station data displays. Date ranges can be selected dynamically, and everything is hosted in the Google Cloud. Because our station data is relayed to the cloud in real time, we have had the opportunity to do some interesting things with it. 2 years ago, we launched an Amazon skill and flash briefing. The flash briefing adds the daily audio forecast to your morning Alexa news and has several thousand users. Station data is also accessible with the Mount Washington Observatory Alexa skill. Anyone can ask what the current weather is or what the weather was for any day since 1935. You can ask Alexa what the weather was on the day you were born or what the weather was when you visited the Mount Washington or traveled on the Cog Railroad. I have a beta version in progress that allows the user to ask what the weather is at a particular station, as well as tell me which stations are offline. It's very convenient to be enjoying your morning coffee and to ask Alexa to do a Mesonet status check. Thank you all very much. I hope you've enjoyed this presentation. Any questions or comments, put them in the chat. Feel free to contact Mount Washington Observatory or myself at any time, and enjoy the rest of the workshop. Thank you.